All right, so for today's ACOM seminar, we have Siyuan, an ASP student, ASP fellow. And you guys, I'm pretty sure you all already know him, but I'm going to give a little bio. So he got his PhD from the Hong Kong University of Science and Technology. And from there, he joined the University of Michigan, Ann Arbor as a postdoc fellow, where he focused on halogen chemistry and air-snow interactions in the Arctic. And then in late 2017, he got the ASP and joined ACOM. And his current research interests include the ocean biogeochemistry control on the atmospheric chemistry, as well as the reactive halogen chemistry in the troposphere and lower stratosphere. All right, let's take it away.
Okay. Thank you very much for the introduction. So today I would like to present some of my previous work, actually. We recently submitted the paper out, so this is actually the first time that I present this kind of stuff. The title of the presentation is Reactive Halogen Chemistry in the Arctic. We have some really interesting new chemical insights based on some recent studies. So this is a work that I did when I was in University of Michigan in Professor Carey Pratt's group. So just a little bit of background. Reactive halogen chemistry plays a very important role in Earth's atmosphere. It partially led to the Nobel Prize in Chemistry in 1995 for their work in atmospheric chemistry, particularly concerning the formation and decomposition of ozone in the atmosphere. So that work was mostly focusing on the stratosphere. The stratosphere ozone depletion is actually one of the greatest environmental concerns of the 20th century, and which was largely due to the heterogeneous reactions involving reactive chlorine species in the atmosphere. But back then, we knew very little about the tropospheric halogen chemistry. Until about 1980s, the first time people observed that in the polar boundary layer, ozone would sometimes drops to all the way from background level all the way to about zero. This kind of ozone depletion events could sometimes last for a day, a couple of days. In some extreme cases, could last for 10 days or so. And then later, people found that this kind of depletion events, ozone depletion events in Arctic springtime, were largely associated to the filterable bromine species. Back then, we did not have all those fancy techniques to measure the speciated halogen chemistry, but instead, people trying to filter everything onto and then take it back to the lab to measure total amount of particulate bromide and HBr in the atmosphere. And now we have learned a lot about the halogen chemistry in the Arctic. Basically, I'm going to take bromine as an example here. The sunlit snowpack would emit molecular bromine species, for example, Br2, into the atmosphere, which strongly absorb visible radiation and would produce two bromine atoms here. The produced bromine atoms can either participate in radical propagation involving BRO and producing even more Br2 and bromine atoms, or bromine atoms could be scavenged by a bunch of different things, for example, volatile organic compounds. So bromine atoms plays a central role in the reactive halogen chemistry. This is literally, I placed bromine atoms in the center of this plot, but it is quite important. And when it comes to actually Arctic halogen chemistry, one thing we have to note is that the snowpack is closely coupled with the atmosphere. So basically, snowpack is kind of like we consider it the pristine and pure, but actually snowpack contains a lot of impurities. For example, it contains salts, containing organics. When you have the sunlight, lots of complicated chemical reactions could occur within the snowpack. So we now have known that the halogen activation within snowpack could be initiated mostly by OH radicals, maybe ozone as well. And also ozone, the presence of ozone can further enhance the halogen activation within snowpack. And lastly, we know that acidity certainly plays a role in snowpack, but a lot of things we still have no idea what's about in the snowpack. So how do we measure halogen species in the atmosphere? So historically, there are two major types of techniques. For example, firstly, remote sensing techniques, especially the differential optical absorption spectrometry, or DOAS, has provided lots of remarkable insights into one of the key species, which is bromine monoxide, as well as the spatial distribution. On the other hand, like in situ measurements such as chemical ionization mass spectrometry, or CIMS, have provided chemical insights into the halogen speciation and recycling mechanisms. And by the way, BRO has been widely observed on remote sensing platforms and also being mapped from satellite, for example, all these different satellites probes. But I would like to make a few important remarks here. Firstly, the remote sensing is not affected by sampling artifacts, which is oftentimes a major concern for in-situ measurements. And secondly, we have to keep in mind that remote sensing is always indirect. Sometimes we rely on retrieval, and you always need to validate the remote sensing results. And oftentimes the results should represent an average of result over a certain spatial scale. And lastly, satellite VRO, it's really a column observation. There's lack of vertical resolution, and sometimes people you may see people report like troposphere column of VRO, whatever. They have to work really, really hard on that to get that fraction right. So why do we care about halogen chemistry? So the importance of halogen chemistry in the atmosphere are mainly twofold. Firstly, affect ozone. Reactive halogen chemistry catalytically destroys ozone, and ozone is a pretty important greenhouse gas, and in fact the oxidative capacity of the atmosphere. When it comes to the Arctic or the polar regions are particularly sensitive to the global climate change and has larger contribution of radiative forcing from ozone, because firstly the polar regions are largely covered by ice and snowpack, and hence has much higher albedo. And secondly, you don't have lots of water vapor up there, so water vapor is another very important greenhouse gas. And also in polar regions is oftentimes cloud-free. And lastly, we have the albedo effect in Arctic regions will amplify the effect. Another importance about halogen chemistry is that atomic bromine actually largely controls the chemical transformation of atmospheric mercury, which is a toxic gas and bioaccumulative. So long-term record in the Arctic indicating that Arctic snowpack is actually a net sink for atmospheric mercury, introducing the toxic material into the ecosystem. And atomic bromine, unfortunately, has never been directly measured due to tremendous technological difficulties. Alternatively, people have been using different other type of methods to infer the atomic bromine levels in the past. So in this work, we're going to present the first, very exciting, the first direct measurements of atomic bromine measurements in the atmosphere, which was conducted in the Arctic boundary layer using a chemical ionization mass spectrometry using the University of Michigan the chemical ionization max spec in Professor Carey's press group. We recently submitted a paper to PNS and just got the feedback, which are fairly positive. So, and just a little bit of results here. The measured atomic bromine levels reached up to 14 parts per trillion. This is a remarkably high level if you know anything about atmospheric chemistry or halogen chemistry at all. This is pretty exciting. And what's even more interesting that atmospheric mercury and ozone depletion are now quantitatively explained by the atomic bromine measurements. And when it comes to, especially regarding the mercury, this is the first field evidence of the bromine-induced mercury oxidation. All right. Now let's take a little bit look at more about the details. So this University of Michigan CIMS instrument using iodine water cluster to measure as a reagent iron to measure a wide range of halogen-containing species, and has fairly low limit of detection for a number of these species. And one important thing about, like I mentioned before, like sampling artifacts could be a major concern for many of these like sticky gases. So in this work, we use a donut, which is a specially designed sampling inlet to minimize the wall loss and sampling artifacts. So basically how this thing works is that it's a sampling tube about this long, and it has a literally donut-shaped thing attached to one end, and the other end is directly hooked up to the CIMS instrument. We use a blower to maintain a well-defined, very high flow rate, and previously people ran internal experiments and found that there was no apparent evidence for the turbulence within this sampling tube. That means the sample air within this sampling inlet is not touching the inlet wall material. Moreover, the CIMS inlet is actually sampling a subflow sitting right at the center of this inlet, so further minimizing the possible inlet artifacts. So this similar inlet has been used to measure a wide range of reactive gases such as nitric acid, ammonia, and HOBr, BRO, and CLO. And in particular, Jing, Liao et al., they published a paper and showed that in situ BRO measurements using the CIMS measurements equipped with this inlet are in very good agreement with Long-Pastor's measurements within measurement certainties. So, to sum up, if there is really bromine atoms hanging out in the atmosphere, it should be able to survive the sampling line. And now comes the difficult part, is the bromine atoms calibration. When it comes to bromine atoms, you can't simply go to signal algorithms and go like, hey, excuse me, can I buy a bottle of bromine atoms? You want to do anything about bromine atoms, you have to make it in-house. So the way we do that is to synthesize the bromine atoms using this kind of like flow tube reactor type of thing. We inject the Br2 molecules into the flow tube and shed visible light on it, and this thing could undergo photolysis producing bromine atoms. And then we inject a known amount of acetaldehyde. Acetaldehyde standards from Eric, and we trust Eric, so we should trust the result here as well. And one cool thing about the CIMS instrument is that you can measure different irons. And when it comes to halogen species, we know that, for example, bromine has two stable isotopes, 79 and 81. If you're, for example, if you're measuring anything contains one bromine atom, you should be able to see two peaks with a relative abundance of above 1 to 1. This is a very important way to actually validate or confirm the detection of any bromine-containing species in the system. On that corner, what I'm showing here is an example of what flow tube experiment looked like. On the top panel, the green dots showing the water iodine iron, which is the reagent ion. It looks fairly stable. That means the instrument was happy during the entire time. And then M over Z 285 and 287 are two of the major ions of Br2 molecular bromine. As you can see, in the beginning, we did not have anything in the system, so everything remains at around 0. And at this point, we injected Br2 into the system. As you can see, these two ions are both increasing, and the ratio is approximately 2 to 1. That's because Br2 has two bromine atoms, so the relative abundance of these two stable isotopes should be 1 to 2 to 1. And then the orange shading indicating the time periods when we turn on the visible lights. As you can see, you can see a dip in Br2 time series. That means part of the bromine Br2 molecules were photolysed. And on the bottom panel, we can see the production of bromine atoms. And here, what I'm showing here are the CIMS mass scans. So CIMS mass scans are kind of the mode that the instrument was working in. Basically, under normal operational mode, because this mass scan basically scans all the ions in the entire range. It takes a very long time normally. So when we're actually measuring stuff, we don't scan all the ions, we just scan a subset of the ions that we're interested in. But here, sometimes mass scans could provide very useful information. For example, in this case, M over Z 206 and 208 are the two stable isotopes of bromine atoms. As you can see, as indicated by the black line, if we have only nitrogen, which is the carrier gas, there is pretty much nothing. And if we inject Br2 into the system with the presence of light, we can see the Br2, the 206 and 208 ions are both increasing. And if we also inject a little bit acetaldehyde into the system, we can see this lower because part of the produced bromine atoms are quenched by acetaldehyde. And this plot, what I'm showing here, are the background subtracted normalized signals of the two stable isotopes of bromine atoms. As you can see, it lines up perfectly with a theoretical prediction. This is confirming that we're actually detecting bromine atoms in the system. And when it comes to flow tubes, sometimes the experimental conditions could be very tricky. So in this work, I tried really, really hard to optimize the flow tube conditions. For example, if you're trying to measure anything very sticky or reactive into the flow tube, we have to worry about, okay, what if my compounds is all reacting on the flow tube surface? So in this case, I did a couple of things. Firstly, the flow tube inside and all the glasswares are treated with Salon CT, which is a commercial product. We're supposed to occupy all the reactive sites on a quartz surface. And also the chemical regimes are carefully tuned such that the bromine atoms are consumed by acetaldehyde before it reaching the flow tube walls. So the estimated wall loss influence is is smaller than 1%. And also we possibly may have some contaminations of, for example, NOx or ozone in the ultra pure nitrogen gas. And we're measuring these two things using monitors. They're below detection limits at all times. And even if we put the detection limits into the calculation, the influence of these two things are also much, much smaller than 1%. And lastly, some of the early experiments looking at bromine atoms in the lab, they found that if you could work with higher concentration of bromine atoms, these two things would recombine and produce Br2. If this thing happens, it would mess up our experiments. But we found that under these very low concentration levels, the bromine atoms recombination influence is also very, very small. And everything is validated by a kinetic box model designed specifically for the flow tube experiments. So lastly, this is what a calibration curve looks like. And as you can see, we tried really hard to push the linear range of the bromine atoms down to below 40 parts per trillion. This is an important thing because we expect the bromine atoms in the ambient should be on the order of 10 ppt or something like that. Therefore, if you have a calibration curve ranges up to ppb level and you're trying to calibrate the ppt levels, then could be a little bit hand wavy. So, and also all uncertainties from the known kinetics, from all the flow rates, from the BR to perm source, and from asymptotic standards are all propagated carefully into the error bars. So I'm a modeler now, but this is a calibration curve that I can live with. If we apply this calibration curve into the field observation, so this is this is just an overview of the field observation. This is a Bromax field campaign conducted near Ukartvik, which is previously known as Barrow, which is the northernmost town in Alaska. And the field campaign was between 14 to 28th of March in 2012. This is just a springtime. And a wide range of halogen-containing species are measured using CIMS instrument at a tundra site. And also we have the measurements of ozone and mercury at different locations as well. On the far right-hand side of the plot, what I'm showing the wind rose plot, basically indicating during the entire period of study, the wind direction is basically from northeast and east. So if you're familiar with the chemistry stuff in the Barrow, Alaska, this region indicates basically the clean air sector. That means that the measurements during this period of time is not affected by local anthropogenic activities, therefore representing the background conditions in the high Arctic. And this is the overview of the chemical measurements. As you can see on the top panel, I'm showing the beautiful measurements of atomic bromine and the BRO as well. The measured bromine atoms reached up to 14 parts per trillion on one of the days. And we also have the mercury measurements and ozone and a bunch of other things. During this campaign, we observed 3 ozone depletion events and 5 mercury depletion events as well. On this panel, what I'm showing are the field measurements of the 2 stable isotopes of bromine atoms. As you can see, they both sit, the relative abundance sits right around the 1-to-1 line, indicating confirming the detection of bromine atoms in the field. And one of the concerns about when you're trying to measure the stuff in the Arctic is that whether, for example, the time series you're measuring recorded by the instrument is actually due to active local chemistry, or is it due to the advection? For example, if you see a decrease in ozone, whether the ozone is due to the advection of air masses in which ozone is already depleted. So there are a couple of evidence. Firstly, Bill Simpson published a paper in 2017 that used, during the same field campaign, the authors analyzed ozone and BRO observations at multiple locations on over mobile stations, and they found that basically the ozone and BRO measurements on different locations are actually in very good agreement, and indicating that the spatial scale of the localized region of active halogen chemistry is possibly larger than 30 kilometers. And in another previous studies, they also measured both BRO and ozone on what is so-called O-buoy. Basically, you put an instrument on a buoy and let the ocean, Arctic Ocean, bring those things to wherever they want. And they can measure, they can study the time scale and spatial scale of halogen chemistry. Basically, what they found is that the moderate ozone depletion event, which is defined as ozone concentration dropped to below 15 parts per billion in the high Arctic, are generally widespread at the spatial scale above the 280 kilometers. This is pretty much very light widespread spatial range. And also, this is a satellite image snapshot on March 15th of 2012. The satellite lower tropospheric BRO column is measured by the GOM-2 satellite. As you can see, the widespread lower tropospheric BRO plume are basically the spatial scale look pretty wide. So all this indicates that the active halogen chemistry we're probing here are probably not affected by advection. So actually very active local chemistry is happening. And one very interesting thing about the BR to BR is about the BR to BRO ratio. The reason that we're interested in this ratio is that BRO is widely observed in remote sensing platforms, including satellite. And by looking at this ratio, we can actually connect our institute bromine atoms measurements to those remote sensing measurements. And is also providing implications for the radical recycling mechanisms. As you can see on this plot is that the BR to BRO ratio decreases strongly with increasing ozone. That's because the more ozone you have, the stronger the equilibrium will be pushed towards BRO. This makes perfect sense. And this is reasonably captured by the model as indicated by the shading here. And one interesting that I would like to draw attention to is the color code, the color scale. The color code here is actually representing the ratio between the primary production of bromine atoms versus the BR to BRO conversion. To translate that into human language, that means if you have higher ozone, that means all the bromine atoms produced from BR2 will be efficiently converted into BRO. And actually the ratio is smaller than 1. That means the majority of bromine atoms actually produced via the secondary recycling. On the other hand, if you have this ratio much larger than 1, that means, okay, you don't have enough ozone, you don't have sufficient ozone levels to convert all the BR atoms into BRO. That means the primary production dominates the BRO bromine atoms. And you can see, if you take a closer look at this equation, all these things we can measure from our data set. Therefore, we have actually a kind of like observationally confined radical chain length of the bromine radical system. As you can see, basically when ozone is above 7 parts per billion or so, the ozone level is basically high enough they can convert all the bromine atoms into BRO. That means that implies the importance of the secondary recycling. On the other hand, if you have ozone levels below 3 parts per billion or so, the primary production plays a more important role and the radical chain length might be shorter. So by looking at this ratio, actually we have some sense of the radical propagation mechanisms. So here comes a question. How can we get all those reactive halogen species in the atmosphere in the first place? So there's a term or the jargon that people use is called halogen activation. Basically, in the atmosphere, in the snowpack, in the aerosols, we usually have lots of bromide, which is not very reactive. And what actually matters to ozone and mercury is the so-called reactive halogen species. So the process that convert these bromide compounds into these reactive bromine species are called halogen activation. So the role of HOBr in halogen activation has been highlighted in most, if not all, previous studies. But in this work, we can see obviously it's not like that all the time. For example, this is actually my favorite case study day during the entire campaign. As you can see, in the early morning period, the sunlight, during the early period of time, we see a huge spike of atomic bromine due to very high concentration of BR2. And if you take a closer look at this plot, as indicated by the HOBr measurements, during the morning time, HOBr levels remains very, very low. That means halogen activation occurring in the morning is definitely not due to HOBr. And we see the very strong decrease in mercury, elemental mercury as well. That means it's not the halogen activation is confirmed by the decrease in mercury, which is, again, not due to HOBr. We actually show this kind of phenomenon in one of our previous analyses, basically by looking at the relative importance of these ClNO2 and BrNO2 versus HOCl and HOBr. For example, if you take a look at this panel B, that means the contours shows the ratio between BrNO2 production versus HOBr production. If the ratio is above 1, that means the production of BrNO2 is favored. But if the ratio is below 1, that means formation of HOBr is favored. During the previous field campaign in Bear, Alaska, which is OASIS field campaign in 2009, we have both NOx and HO2 measurements. If we put both these measurements onto a plot, we can see this campaign average sits at around a 1-to-1 line. That means that when it comes to bromine activation, BrNO2 is at least as important as HOBr. But if you take a look at similar things for chlorine compounds, as you can see, ClNO2 is definitely more favored than HOCl. Unfortunately, to this day, we do not have direct observation of ClNO2 or BrNO2, but we have second best thing, which is from the I'm going to show here. So we know that NOx is actively produced within snowpack. And if you have a fancy NOx instrument and if you stick the sampling inlet within the polar snowpack, you will oftentimes see that the NOx levels within the polar snowpack is actually much higher than what you would measure in the overlaying atmosphere. And also snowpack NOx emissions have been directly measured in the Arctic and in Arctic region. And very interestingly, recent studies, they measured for example, these papers, they measured the dual isotope signatures in nitrate in the polar regions. For example, different chemical processes would actually lead to different isotope signatures in, for example, nitrate. And we know that nitrate in the snowpack photolysis would produce NOx. But studies, they have found that, okay, nitrogen has two stable isotopes, 14 and 15. When it undergoes photolysis, the heavier nitrogen atoms would be preferred to stay in the condensed phase, while the produced NOx from the photolysis in the snowpack would actually carry a higher abundance of the lower isotope, stable isotope. And similar things happens to the nitrate as well. If you oxidize NOx into eventually nitrate, if you measure the oxygen stable isotope, and actually the heterogeneous process would produce higher this delta 17O signature compared to homogeneous oxidation via nitric acid in the gas phase. And previous studies in the Arctic, they actually found that the snowpack emitted NOx is systematically associated with the heterogeneous formation of nitrate they measured in the nitrate, which correlates strongly with BRO measurements, implying heterogeneous chemistry of BRO and O2. While in fact, the heterogeneous reactions involving BRO and O2 is one of the very few chemical heterogeneous reactions that would lead to such high delta 17O signature in the nitric content. So although we don't have direct measurements of BRO and O2 in the Arctic, we have a second best thing, which is the confirmation from the dual isotope analysis. So future studies definitely should take a closer look at ClNO2 or BrNO2 or these type of species. And what that means is that we actually, the elevated NOx levels in the Arctic would actually implies extended radical propagation at lower ozone levels. For example, the current thinking as illustrated by this diagram is that when you have lower ozone, so for all the halogen activation involves BRO. If you have lower ozone levels, formation of BRO is not favored. Therefore, the majority of the bromine atoms would be killed by OH radicals, and then the radical propagation just terminates. But we have shown that the rapid recycling involving BRO and O2 and maybe BrNO2 as well can sustain the elevated daytime BR2 as indicated by the CIMS measurements. Basically, what I'm showing here as indicated by the red arrows, that at lower ozone levels, if you have elevated NOx level, we have another recycling mechanism that basically convert a reactive bromine species into reservoir, which is BR2, and the bromine atoms would be otherwise killed by other volatile organic compounds. And some of the studies indicating that BrNO2 may also lead to halogen activation in aqueous system, but we don't know what exactly is going to happen there. More importantly, like I mentioned before, if you measure NOx content within snowpack, the concentration levels is oftentimes much, much higher than that in the atmosphere. That means this type of mechanism may play an even more important role within the Arctic snowpack. Therefore, basically, this implies that extended radical propagation at lower levels sustained by higher elevated NOx content. And now I would like to shift gear to talk a little bit about another compound, which is mercury. So mercury is really a global pollutant. It's widely emitted from a bunch of anthropogenic sources, for example, burning garbage or this type of things. And the majority of mercury emission is in the form of elemental mercury, as indicated by mercury 0 here. So mercury 0, or elemental mercury, is fairly insoluble and very stable in the atmosphere. And so far, the only known efficient oxidation pathway is a reaction with bromine atoms. And during the bromine oxidation, the mercury 1 is produced. This thing is very unstable and could be rapidly scavenged by a number of other molecules producing mercury 2. Mercury 2 is oftentimes called as oxidized mercury, which is very soluble, and the deposition is the major pathway of mercury entering the ecosystem. Unfortunately, the BR-induced mercury oxidation kinetics remains highly uncertain. It's very difficult to measure this type of things in the lab. And also the molecular identity of the products remains highly unclear. That means many of these things are, at this point, remain operationally defined. So during the Bromax field campaign, we actually captured 5 of the mercury oxidation, mercury depletion events. For example, this is an example, as indicated by the red shading here in the early morning, that we have a huge spike of bromine atoms. And then the elemental mercury, as indicated by the black lines, decreased strongly, and which is accompanied by the increase of the products, which is mercury 2. This implies the local active halogen-induced mercury oxidation. And interestingly, all these oxidation events occur in the early morning when the boundary layers were extremely stable. And if we put the 5 of the mercury depletion event on one plot, on the y-axis, what I'm plotting here is the observationally derived elemental mercury lifetime as a function of bromine atoms concentration. As you can see, the more bromine atoms we have here, the shorter chemical lifetime mercury is. And this is really cool, and also indicated by the shadings indicating the calculations based on known chemistry. As you can see, it's reasonably captured by the models. So this is the first field evidence of bromine-induced mercury oxidation. Also, it provides a pretty unique pathway to validate the highly uncertain mercury chemistry. And lastly, I would like to leave Arctic just for a little bit to mention a little bit about the potential implications in other regions. So we think that bromine atoms may also play an important role in this region, that it's tropical transition layer, or TTL. So model simulations suggest that bromine atoms is possibly the dominant daytime inorganic bromine species in the tropical transition layer during daytime, in this region where bromine chemistry has a profound impact on ozone and mercury, and also ozone radiative forcing and climate feedbacks in the lower stratosphere. So this is a plot created by Alfonso Sanz Lopez's group and using ChemChem. As you can see, nice illustration of the existence of a possible tropical rings of atomic bromine. The existence of the layers of bromine in this region is due to the relatively lower ozone level and the very low temperature in this region. So why do we care about this region, or bromine atoms in this region in general? So the tropical transition layer it's a gateway of the troposphere to stratosphere in transport of a number of, for example, halogen-containing ozone-depleting substance. One of them is a very short-lived substance. Don't be tricked by the name. It's called very short-lived, but the shortest lifetime in the troposphere is on the order of a couple of months. But once they are transported to this interface between troposphere and stratosphere, the UV radiation gets stronger, and these things starts to release bromine atoms. So the current best estimate of very short-lived substance contributes about 5 parts per trillion of total stratosphere BRY, of which about half is in the form of inorganic bromine. And these things are very sensitive to dynamics and wet scavengings as well. On this plot, I'm showing a plot from the Zalavich's paper published in 2015, basically showing all the BRO column measurements in the stratosphere and compared to different model simulations. If we only include the model simulation of the BRY production from the long-lived halogen-containing compounds, we simply cannot explain the observed BRY in a stratosphere. But if we start to include about 4 to 8 ppt of BRY from very short-lived substance, we're getting much closer, especially if you look at the tropical regions, the agreements gets much better. So we think that maybe bromine atoms in the TTL may provide a key constraint of the BRY injection into the lower stratosphere. So it's going to be very difficult to measure that stuff, but I'm just going to put out here. The implications is extended certainly beyond the Arctic region. So the summary here, we report for the first time the direct measurements of atomic bromine in Earth's atmosphere, which is conducted in the Arctic boundary layer, leading to mercury and ozone depletion. And secondly, this technique may be one day used to probe the tropical rings of atomic bromine as predicted by model studies, which may provide a key constraints on the ozone depleting substance in the lower stratosphere. And with that, I'd be happy to take any questions or comments.
Any questions?
So are there any plans to actually put the CIMS on an aircraft and fly into the TTL, or is that?
I myself don't, because
Yeah.
I would love to. But there are some difficulties. For example, it might be difficult to, so the inlet issue is very difficult to resolve at this point. If you really, and also if you look at the prediction from Alfonso's group, the maximum concentration is maybe like 1 parts per billion, 1 parts per trillion, which is very close to our detection limits. But we can't rule out maybe in the future there are more sensitive instruments out there and the inlet issue might be resolved. So in this inlet we have the inlet we're using in the Arctic, the residence time is like 0.02 second or 0.002 or very, very low number. But on the aircraft, it might be very tricky to minimize the sampling artifacts to this level. So maybe difficult, but maybe plausible.
Anybody else?
That's nice that you showed that the chemistry was happening locally. Could you speculate on on how representative that site is? You know, when you think about the Arctic in general and out on the sea ice and things like that, can you speculate on that?
So that's a really hard question. So far, there are a couple of locations in the high Arctic region that received more attention. For example, Bear, Alaska is one of them, and a couple of locations in Greenland and also Svalbard, and I think maybe a couple of sites on the Russian side as well. All these different locations show up very different things. For example, like NOx levels in all these regions are kind of different. Like usually in Greenland, the NOx levels are slightly lower, but in Bear, Alaska, it could be slightly higher. Another very important difference is that the coastal regions versus sea ice covered regions and versus inland regions, they represent completely different conditions. And if you look at going back to the first slide showing the satellite measurements of BRO, as you can see, the satellite measured BRO plumes are mostly located near the coastal regions. There are some recent studies indicating that these higher levels of BRO plumes could be measured way inland as well, but we just don't know any. I mean, it's really hard to tell whether this type of things could occur very far away. And because in order to produce all the bromine things, you have to have bromide in the condensed phase in snow or particles in the first place. That's why the coastal regions are easier to get all those things.
I know at one time there was a lot, when we were doing OASIS and soon after that, there was a lot of talk about the satellite measurements of BRO and how good those satellite measurements are and were. What has happened in the last few years with that? What is the current thinking of how representative those measurements are to reality?
So I am not a satellite guy, so I can't comment too much on that. But in the Arctic region, as you can see, there's a huge chunk is actually chopped off because satellite simply doesn't have coverage on the very high Arctic region. And also a current thinking is that maybe these plumes are largely located at near surface, because in order to propagate all these things into the lofted layers, it's going to be very difficult. But recent studies, they put those instruments on aircraft and flying around in the coastal and the inland regions, they actually found lofted BRO layers, implying that propagation might be more active or more stronger than we previously thought. So maybe part of the plume is lofted, but like satellite measurements can't really do that kind of things. Yeah, so yeah.
Anybody else? I just had one question, actually. Can you go back to the TTL bands? I think I missed it, but why there were 2 of them?
Yeah, that I'm not very sure.
Oh, just 2. Oh, okay. Just 2 separate. Okay. All right. Okay. Thank you.